Hey guys, let's have a little crash course on all the theorems that have to do with differentiable functions and some continuous functions. So we're going to try and make this one really quick. So we have four theorems, three really, one's an extension of the other. We have the intermediate value theorem, mean value theorem, and Rolle's theorem by extension, and then the extreme value theorem. So if we're first looking at the intermediate value theorem, it says that f is a continuous function. And if we're looking at it on the closed interval from a to b, so we have a start and we have an end. So we're starting at a and we're ending at b. If there's some y value that is between the y values f of a and f of b, so if there's any y value d that's in between those two y values, then there has to be a c, which is an x value, that lives between a and b. So we can't, if the function is continuous, we can't just jump from this point to this point without going through every y value to get there. So we cannot go from the y value f of a to the y value f of b without going through every y value in between them, or else the function wouldn't be continuous. So intermediate value theorem, not that difficult. It's just ensuring that in order to go from one point to another, we have to touch every point along the way. Rolle's theorem, which we're going to talk about first because it's that special case. So we have three conditions. The function has to be continuous. We have to be able to take the derivative, and if the endpoints have the same y value, so our endpoints have the same y value, there is going to be some c value between a and b where the tangent line at c is equal to 0, or the tangent line of at c is horizontal. So the derivative at c is equal to 0. The mean value theorem, it has those same two stipulations. So f is continuous, so we can draw it without picking our pen off the paper. F is differentiable, we can take the derivative at any point from a to b. And it says if we connect those endpoints, so if we found the slope between those 2 points, so our average rate of change, then there is some x value between a and b. So here's a, here's b. There is some x value between there where those slopes of the tangent line and the average rate of change are equal, or these lines are parallel. So here is c, and f prime of c is equal to that slope. Extreme value theorem, if f is continuous and we have a closed interval, so we starting at a and ending at b, then f has both a maximum and a minimum value. Now it doesn't mean that we have to have a relative max and a relative minimum, so our slope does not have to be equal to 0. We don't have to have a critical point on that interval. We just have to have a maximum and we have to have a minimum. So here would be our minimum and here would be our maximum. So there's a largest y value and there's a smallest y value. Just thinking about the relationships between the derivative and the function. So if we're on this part of the function, our function is increasing. The slopes, all of the tangent lines on this interval, are positive. So if the function is increasing, the derivative is positive. So function increasing, derivative positive. Our derivative is equal to 0 because we would have a horizontal tangent line. In this interval, the function is decreasing, so our derivative is less than 0. So function decreasing, the tangent lines have a negative slope. Again, our derivative is equal to 0. Function increasing means derivatives greater than 0. So increasing, derivatives greater than 0. Just making a note about this point, that at this point the function is not differentiable because we would have a bend in that function. Another way to think about that is we wouldn't know how to draw the tangent line at that point. So we have a bend, so our function is not differentiable at that point. And then this last piece over here, the function is constant. So it's not increasing, it's not decreasing, the function is constant. And if the function is constant, then the derivative is equal to 0 because this is a horizontal line, and the slope of a horizontal line is 0. It gets a little trickier when we're looking at a picture of the derivative. So if we're looking at a picture of the derivative of the function, then we have to think about what does the derivative mean in the context of the function. So I'm going to break this up into a couple of parts. From, from 1 to 2, our function is decreasing because the slopes are negative. Another way to think about that is that they're below the x-axis. So if the function is decreasing because the derivative is less than 0. Here we have our derivative equal to 0. The derivatives everywhere along this interval are positive or above the x-axis, so the function is increasing. Again, the derivative is equal to 0, and function decreasing because our derivative is below the x-axis or less than 0. If we wanted to identify what these points would represent, this point would represent, well, the derivative changes from negative to positive. So if the derivative changes from negative to positive, the function decreasing to increasing would be a local minimum. At this point, the function's changing from increasing to decreasing, slopes go from positive to negative, we have a local maximum. And at this point right here, the derivative is changing from increasing to decreasing, so we would have a point of inflection because our derivative is changing from increasing to decreasing. So one of the most common mistakes is that when we're given a picture of the derivative, it asks us to find the local maximum, and we want to say that the local maximum happens right here, but that's not because we're looking at a picture of the derivative, and the derivative changes from positive to negative at 5. What is this point? It's that point of inflection because our derivative is changing from increasing to decreasing. All right, guys, thank you.